This is about the MMC infinity queuing model. We have interarrival times that are exponentially distributed. Service times are also exponentially distributed. Multiple servers, so we have C servers. The queue capacity is infinite, so K is infinity. And this is the flow diagram. So here we see that the service rate is going up in the number of customers in the system, until the point where the number of customers equals the number of servers. If there are even more customers in the system, then the service rate is not going up anymore, because in that case there are customers in the queue. Rho is still defined as lambda over mu, but for this system it's not required that rho is smaller than 1. The workload can be divided over the servers, so now it's required that rho divided by C is smaller than 1 in order to have a steady state solution. We can use the flow diagram to determine the steady state probabilities. We are not going to derive that, but here is a formula for P0 that we can use. So this formula gives us the probability that at some point in time there are no customers in the system. Only this first part is part of the summation, and then after calculating the summation we need to add that second part, and then everything needs to be raised to the power minus 1. The outcome for P0 can be used to calculate the expected number of customers in the queue. So for that we have this formula. And then if we have LQ, then we can basically also calculate the other performance measures that we have. An example, so we will consider an MM3 infinity queuing system, so 3 servers. We have time between arriving customers is 5 minutes on average, and the mean service time is 12 minutes. What we would like to do is we would like to determine the mean number of customers in the queue, and we would also like to determine the mean waiting time. So let's do that. What can we write down as a first step? We first have to choose the time scale. So if we say that we are going to do everything in hours, then we have arriving customers. Mean time between arriving customers is 5 minutes. So we have 12 customers arriving per hour. And service requires 12 minutes. That means that we can serve, for each server, we can serve 5 customers per hour. So mu is equal to 5. C is equal to 3. That's the number of servers. And we can also give rho, and rho is equal to 12 over 5. It's larger than 1, but the rho divided by C is smaller than 1. So this system has a steady state solution. We can also write that down. So rho divided by C is 12 over 5 divided by 3, so that gives us 4 over 5. That is smaller than 1, and that means that there is a steady state. So the system does not explode. Queue length does not explode. Then the first thing that we can do is calculate P0, and based on that we can calculate LQ. So in order to calculate LQ we need P0. So P0, we have the formula on slide 3, and then we can plug in everything. So we start with the summation. We sum from I is 0 to C minus 1. So C is 3, so I has values 0, 1 and 2. If it has value 0, then we get rho to the power 0 is 1. And 0 factorial is also 1, so the first term is 1. The second term is rho to the power 1, so it's 12 over 5, and that's divided by 1. And the third term is rho squared, so you get 12 over 5 squared divided by divided by I factorial is 2 factorial is 2. And then we also add that separate part, so rho to the power C is 12 over 5 to the power 3 divided by C factorial. So 3 factorial is 6, and then times 1 over 1 minus and then rho divided by c. We already calculated the rho divided by c. That was 4 over 5. And this to the power minus 1. The number within brackets should be larger than 1, because otherwise the probability P0 will not be smaller than 1. If we calculate it, then we will find that it is equal to 89 divided by 5. And that raised to the power minus 1. And that's indeed a number in between 0 and 1. So this is the probability that there are no customers in the system at an arbitrary moment in time. And then the second formula can now be used to calculate LQ. So LQ, the expected number of customers in the queue. So let's see what we have in the formula. We have rho to the power c plus 1. So it's 12 over 5 to the power 4. C plus 1 is 4. Divided by c minus 1 factorial. So that's 2 factorial. And that is multiplied by c minus rho squared. And c minus rho is 3 minus 12 over 5. And that will be squared. And this should then be multiplied by B0. And that's equal to 5 over 89. This can be calculated and we can give an approximation is 2.5888. So this is the expected number of customers in the queue, approximately 2.6. The question is to find the mean number of customers in the queue, so that's what we now already have, and we would also like to have the mean waiting time. We have Little's law, so we have that LQ is lambda times WQ, and that implies that WQ is LQ divided by lambda. So if we would like to calculate WQ, then we are going to divide LQ 2.5888 by 12, and then we get approximately 0.2157. Here we talk about time, because this is the expected time in the queue. So here we talk about hours. Maybe better, because this is not very informative, better to transform this to minutes. So this will be 12.9 minutes. So again, expected number, mean number of customers in the queue is 2.6 and the mean waiting time is 12.9 minutes, so almost 13 minutes.